that for me? The candy? Oh, that's so
There's
nice.
some candy down there. I'm throwing a piece.
No, it's okay. I just wanted to steal candy.
Yeah.
All right. Okay, well, you can tell I'm in the festive mood, right? It's wearing a black shirt. That's very spooky today. Wait, so when you went in to buy that, did they give you this? No. Okay. So today we're gonna be thinking more about how waves propagate through mediums. So we already had this example where we were asking the question about whether or not the fish can see us. Remember that? I know it was almost like 7 weeks ago. Right, so much has happened since then. So we're gonna start off with this idea, because this is a homework problem. We'll just get our brains cooking. And then once we're in full working mode, we'll say, okay, let's take the non-easy example and let's bring light in at an angle. And we'll see how the light propagates afterwards. And I promised you we were gonna derive Snell's law. I hope we'll get to that today, because otherwise we'll start to slip. But ideally, we'll get to deriving Snell's law from these principles. And eventually, we'll talk about what happens when you have light propagating in a medium. So for example, inside of something that may have currents or charges. Okay. Okay. Question before we start? All right. Everyone's awake? All right. 3 people awake? Good. 3 out of 6. That'll do it. All right. So one thing I just want to remember, we should think about a reminder when we think about intro physics, right? So imagine you have something like a stick like this, and imagine you have a string attached to it, right? So if the string is attached to it, and there's like a little ring around it that can go up and down, the edge is not fixed. Okay, and I like do like this, and I send a pulse all the way down. What happens to that pulse at the very end?
And like the little ring go up and down.
Okay, and then what happens afterwards?
Should we turn to the initial position?
Yeah, the ring goes up and down. Good. What happened to the incoming wave?
Close to the center. It stops there.
Just stops. Put your hand for just stops.
No, this one will go back.
Why would it go backwards?
Like in the wall, so.
This isn't a wall, right? String.
But I mean, attached to that one.
Okay, so it's attached to little pull things. So let's say, okay, this thing comes in, right? So the ring goes up, the ring goes down. And that's still going to affect the string on the left, right? So now it sends a wave backwards. Okay, so here's the question. Okay, is the phase the same? Is it flipped? Same, right? Yeah. So as it comes in, it's going to force it up, and then it'll go back down in the same way, and it'll force it back in the same direction, same phase. What about, so in this one, okay. What about this one? What if I fix it? Right. Send a little whip of the string, then it hits it and it's fixed. Now what happens? It is inverted. Why is that?
Second part is fixed, so you can't allow it to go up and down.
Yeah, so the second part is fixed. So as this piece comes in and it hits here, right? It's forced to flip around in order to send it back in the other direction. This is okay. And an important thing, the reason that I bring this up at all Because we're thinking about this going through different mediums. Now, this is an example of reflection, perfect reflection in either of the two cases, whether it's able to move up or down, or whether it's fixed. But one thing we want to keep in mind is imagine that on this example, there's one wire or one string on one side that's very light and one on the other side that's very heavy. So what property of a wave between the two sides, like this, that's the heavy one, okay? What property between the two is going to be conserved on both sides? I don't necessarily know momentum yet because there might be some that goes backwards, some that goes forwards. What's that? The frequency. Yeah, why does it have to be the frequency?
The only thing that's right is the velocity itself. It will only change the amplitude.
Yeah, I guess another way of asking this, well, why not the wave? Why not the distance between the waves? Maybe less obvious, but once you see it, you're like, oh, of course. Okay, on this side, I have a wave coming in. It's attached to a heavier rope. Okay, so the wave's coming in. There is a property that's shared on both sides. Aaron already correctly pointed out that it is the frequency. I said, what is the physical reason that the frequency is the same? Because why couldn't it also be, say, the wavelength? Yeah.
It'd be like one of the Newton's laws, like it's not being acted upon, so it keeps the same.
It's even easier than that.
Um,
This is when you see it, it's going to be so obvious to you. What does frequency mean again?
Singular frequency over two part.
No, but like intuitively. You're absolutely right, but like, what is it? Like, let's explain it to our cousin who doesn't know anything about math. We want to take it really back to basics here. So no Newton's law, just like definitions and thinking physically what's happening here.
How often something happens?
Good. How often what happens?
A wave? Or a peak?
A peak. Okay, good. So the frequency is describing how often I go through an entire undulation. I go from peak to peak, right? Okay. So let's look here at this physical situation. They are connected, are they not? They're moving up and down together. Why do they have to share frequency?
One's moving the other.
One is moving the other, and they are literally like when this one goes up and down, that's the frequency going up and down, it's pulling the other one, it's forcing the other one to move. Now, what can change afterwards? We haven't discussed this yet. Maybe power, maybe momentum, maybe wave number, how big that wave is, depending on how it's propagating through the medium. But they are forced to move at the same time because they're physically connected, right? Okay. So that's the only thing that I'm going to really write down that's important here. And we'll see this more important as we talk about our fish example. Okay, so just a little reminder. We had this example. One side, we had some medium like air, and on the other side, we had some medium like water or plexiglass or whatever. And we wanted to make some definitions. And I wrote down something like R. What was big R in the last class? I know I use letters all the time, so it's okay if you don't know where it is.
You don't have a name, but it's a ratio to intensities, I think.
Exactly right. So this is R for reflected energy fraction. And that would be the incident the intensity of the reflected beam over the intensity of the initial beam. Okay. And I said this could be written as the amplitudes of each of these. This is the reflected one. And then this is the incident one. And there was some other stuff that like fell out. Do you remember the definition of intensity? Okay. And then I didn't show you, but it's true, that this can also be written as N1 minus N2 over N1 plus N2. Right. Okay. Now, does this make intuitive sense? Maybe not. This comes from a derivation. This here, this second part, this requires that mu1 equals mu2 equals mu. And that's generally true in most mediums. It's really the permittivity that's going to change. Epsilon 1 and epsilon 2, the ones that are changing mostly, not this. Okay. So if the mediums are the same, if N1 equals N2, you have a reflected wave.
And when we, yeah, but.
Yeah. No.
Then it's the same thing.
That's the same thing, right? So this would be N1 minus N1, 0, and there'd be no reflected wave. That's why you don't have simultaneous reflection in the same medium. Only when you go through mediums that you see reflections. Okay, and then I asked you to find this thing. This one was the T stand for? Transmission, yeah, exactly right. So this is the reflected fraction, and this is the transmitted fraction. So let me write that underneath. Okay. This is the okay. And this has some other pieces too, but the piece that matters most to you. Okay. Does that work in the limit that N1 equals N2? Does it?
Oh.
No or yes?
Okay, so we'll find out.
All right, let's do the top, right? N1, N1, N1 squared. Bottom, N1 plus N1. 2N1
Yes.
squared. Okay, 4N. Good thing I wrote it right? Okay, I just copied it down properly. And what's the property between R and T? Constant, right? Why? What is that a statement of?
You can have any more refracted energy than the original.
Sorry, say that again?
You can't have any more refracted energy than the original.
Exactly, right. It's a conservation of energy statement, right? So it says everything that we put together here has to be accounted for. We love accounting in math, right? All right, and so this took us to our fish problem. And I know, yeah,
You said conservation of what?
energy. Right? Because these are the intensities. And what's an intensity? Better define that. Let's write that.
Foster farms. It's important when you're at this level.
Is that good?
That dot product or?
Ah, shit. Okay, here we go. Little dot, tiny dot. Okay, so it's area times time. So this is saying how much power am I delivering per unit area per unit time? Oh, what's power? Yes, something energy what? That's good. Okay. Make sense? All right, so let's do the next one here. Let's do our example of the group work. I have a fish. Okay. I have, it's in water here. And then there's plexiglass. I'm just gonna call it glass. And then there's air. Okay, and I have an eyeball. You'll draw your eyeballs that way, right? In physics. Okay, so I'm looking at the fish. Okay, and I'm imagining light is being it's coming off of the fish, some incident light is coming off the fish. And my question is, you know, how well do I see the fish compared to how well it sees me? Okay, so I'm gonna wanna compare, for example, the reflective fractions in both. Does that make sense? Okay. So let's do it. This one has N1. This one has N2. And this one has N3. Yeah, all right. So what was the question?
How well can you see the fish?
Compared to?
How well the fish sees you? So.
We're finding all the directions of everything in each medium.
Right, yeah, we did that already. We found all the directions. Okay, so we can find out that there was reflected ones. So let's first write all those down. So how many times is this initial incident wave? Okay, say E naught I. What happens to it? How many reflections are there? What do I have to consider? Because now I've given you all of the items that you'll need for this problem. But knowing how to attack it is perhaps not so obvious.
Functions,
Two reflections, where?
both the boundaries.
Both of the boundaries, okay, so we have one here. Okay, so I'm gonna go EOR. And then,
One eyeglass in there.
yeah, so one you have here, maybe going backwards. Call this,
Or two.
yeah, let's call this R1 then, and then call this OR2. And we'll call this OI1. Okay?
Yeah.
Sucks, but it's okay, right? All right, and then what else do I need to know?
And then how it comes out of into the class.
Where, here?
Yeah.
And what am I writing?
Is that-
The transmitted version, right? So let's call that EOT1.
From glass.
And then from glass to air, you have. Okay, and that's the version I can see, right? Okay. So now what do I do?
Like B and D do. Leave that.
Yeah, that's what B is.
Is there another one?
Well, I'm gonna assume that it's just like perfectly good for it.
So one of the things we want to ask ourselves is, I want to know how much light I'm getting from the fish. Okay. That's my question. How well can I see the fish? And to do that, I need to know how much light I'm losing. Right? So I would want to know something like the transmitted, right, which is written over here. And it's written in terms of eyes. And I wrote the eyes up here, and there was hidden in here this E's. So your question was about, okay, we have these E's going back and forth. That's why we did all this wave shit, right? But we also knew that there was a relationship between E and B. These two components, right? They were like this, they moved in phase, and one was something times another. Remember? There's a way to relate E and B. The amplitudes of both were related by something. Remember that? That would give you the power.
Sorry, could you repeat that?
Yeah, is there a way to relate E and P for waves? Electromagnetic waves.
Not the pointing, right?
That's how you would derive the original equations, yeah. But once we get to the amplitude, we're just talking about the amplitudes here, right? We said that we could write E naught as B naught with something. What?
Hands on
You
the-
said all you guys.
Yeah, so God forbid, we read or we wrote it down, lectures online, all you guys, I'm not gonna do any of the own learning, right?
I don't know, all I got is B squared equals 1/C² times D squared.
Okay, look, that sounds pretty good. Say that again. For the people in the back. B squared equals,
1/C². Or you can do like the ratio. Yeah.
okay, so what are we gonna get rid of here?
Are we solving? What are we
Just square
solving
root
for?
it.
Yeah, just square root the whole thing, right?
Yeah.
I'm gonna make it more general here, I'm gonna say V. Okay. And this is what I wanted.
Oh, cool.
This is what I care about. Right, so your question about, well, why aren't we finding B's? Well, because I know what B's are. As long as I can understand the conditions for E, I'm given the B's for free. Right, because they're related, remember that the reason why this is working at all is because this is our direction, K, right, it's headed in that direction. E and B, we know that they have to be oriented like this, E is up and B is out in this specific configuration. But of course I can rotate my hand like this. And so the thing is, because they are in phase, right, and they're doing this together, we know that the properties of the waves themselves have to be the same. The omegas and the Ks, they follow that same solution because we required that for the wave equation, right? So as long as their amplitudes are related like this, which we derived 2 classes ago, we're good. Okay, so we're gonna only treat the E components here because we have nice boundary conditions on the E components. We're gonna come back to those boundary conditions in a few seconds. Okay. So, what are we gonna do here? Where do we sell this one? I ultimately want T in region.
Is that R plus T equals 1?
Okay.
Can you do something like R1 plus T1 plus R2 plus T2, something like that?
Or like,
What did you mean by R plus T equals 1?
if you want to know what they are, then at least you know that they're gonna equal 1.
Okay.
They use one part.
Yeah, maybe I should write this differently. So instead of saying just T3, right? Like what is the T, what is the transmitted fraction that I'm getting from the fish? Yeah, let's do T total, very good. Better words, okay. You see the difference? Because it's not just that I want only this one, I want to know the whole thing, I wanna know the compound system.
But our final answer is just,
Yeah, I'm moving this off to the side, I want this. Okay, so spend 3 minutes looking at your notes and seeing if you can construct a plan, and then I'll start doing it with you.
our final answer is the total, right?
Well, it's the transmitted fraction total. So we're not gonna know what the original amplitude was, but I want it in some fraction of the original amplitude, considering the fact that I have all of the ends. Okay. Okay, spend like 5 minutes thinking about it.
Really stuck to the paper.
Trick or treat. You don't have your custom on that.
Yeah.
He's a skier.
I like that.
Yeah,
It's concept.
you end up food apart, possibly.
Oh,
We're gonna be aliens.
I never said aliens didn't exist, I just said they didn't visit us.
I thought you said they don't have real.
No, very clear on this point. Aliens most certainly exist somewhere in the universe, but they've never come here to tickle someone and then leave.
They do come to teach you and
Sometimes, yeah, sometimes.
I mean, we don't know if they have.
No, we know that they haven't.
how, I knew.
Guarantee it.
I knew,
Guarantee.
I knew 100%.
You can never be
No.
100% sure.
You can be as certain as possible that when I drop this, it'll fall, right? I was told with these ones too, they're like, oh, they're stronger than normal chalk. Like they show this in the ad, they drop it on the ground, it doesn't break. That's a lie.
Yeah.
No, you can be as confident as you can be in anything else in the world that aliens have.
Hater.
Haters, hater.
Yeah.
That's one way to deal with someone else's belief system, sure. Just call them a hater.
Have a little one, have a little, just like,
I don't need to wonder about fake things. You know, the world is beautiful, the world, even thinking just about how light propagates every time I drive to work is wondrous enough. Looking at how it scatters off of clouds, that's amazing. I don't have to like imagine that my butthole's gonna get tickled by an alien.
That's great, yeah.
This is the only thing they report, right? People in Iowa, they're like, oh, I got probed. Like, no, you didn't. No, you didn't. No, you didn't.
All people, aliens are gonna probe is gonna be some random fucking guy.
That's my favorite graphic to show people is all of the alien reports, right? They're just the US.
Yeah.
They're just the US. So aliens come here and they only visit us and a little bit of Canada.
Aliens have taste.
Come on.
Yeah.
No, it's a cultural obsession.
actually, I think maybe it's because, in other places, they think it's like more spiritual or religious phenomenon,
Yeah,
you know, then so it's not maybe.
Oh.
right. Well, so this is how we just ascribe it.
There, I
differently,
also
right?
don't think that
I
like,
feel like
there's
I've been
been-
used it before.
I'm just
No,
saying-
I'm not imagining that you do,
Yeah.
right? I'm just saying that like generally speaking, we can have wonder in the world, but we don't have to wonder about things that are inherently not scientific, right? So it's like, it's okay to be like, there are so many cool things to think about. That like people's cold stories about whether the, you know, Earth is flat or there's an ice wall in Antarctica, like, you know, that doesn't do anything for me.
Teach their own.
Exactly, right, teach their own, you know, believe whatever stories you wanna believe.
I did something cheeky.
What's the guy?
I just subtracted R to the other side of that equation. So if we know it's like reflectance, and we subtracted from one, then we know what T is, so don't we just need to focus on R?
Okay,
I thought you didn't know that art is that facing up.
yeah, so so the question is, it's the counting, right?
Mhm.
And so what I'm asking mostly for here is a relationship between the initial and the final. And so what I'd like you to think about is how I'm gonna write that total fraction. This is for a single.
Oh, that's for a single, like, only a single factory? Yeah, okay.
And we just like, you just add them, like, once you get like, so that first one is for like. Transmitted from like T1. Can you do the same thing where now like, it's not N1 and 2, it's N2 and 3. And then just add those two, or is that like, none?
Okay, so let's,
Yeah,
do we wanna start talking about it right now?
yeah.
Alright. So the total original intensity is split into parts that comes back into region one. Okay. This piece, bounces, comes back. This piece. Bounces, some of it goes through. We're not gonna go that far. No, it's my tough. I'm good forever. Okay. Alright. So, let's think instead about the ultimate question. Okay. Let's write it here. We want the transmitted intensity. Over the initial. Okay. And I'm gonna write that a different way. I'm gonna write that as I. That's this piece in this region, the T3 over the initial I, little I1. Yeah, sorry, that's S. Okay. And then how can I write the intensities?
Want the one with the E? It's like 1/2. There it is.
There it is. Yeah, just point to your page.
Oh, just the E.
Completely ignoring the class.
I don't know, I'm just asking, this is the question that I'm asking. How much light did I get? Compared to how much light that I started with? Right, I haven't yet said how I'm gonna find these things.
Oh,
Okay, we're gonna get there, but I need to set up the problem correctly. To know what I need to know. So the first thing I wanna do, if I wanna know the transmitted fraction, is I have to think about what that means, the transmitted fraction. The initial amount of light goes on the bottom. And the amount that I see with my eyeballs goes on the top. And then I need to define them. And then I look at them and I say, oh, wait. Now I need to know how ET3 relates to this other stuff. Okay. Okay, so what were our solutions for E and for B? Just generally?
Just mess around with that, or,
Yeah, what was the way of it?
okay, that.
One, do you have the E?
Mhm.
And then E naught, E. Will E to the I. Parentheses, ED minus omega 3.
And generally speaking, we could do a plus minus here, right? The omega in both directions. What about B? How do I write that in terms of E?
Same thing. But replace the big E's.
The big what?
The big E's with B's.
What's
You have to-
E versus B?
So it's just.
Oh, just kidding, so they're not like that.
We're just-
Sorry, replace it with that, yeah. Okay. But I mean, that was like one step.
Yeah. I had 50 either. Just backwards. Okay. What are the relevant boundary conditions here?
index of refraction for glass, air, and water?
Two,
Is it the index of refraction for glass, air, and water?
why would those be boundary conditions?
I don't know.
What are boundary conditions mean again?
Well, it's like, it's right at the edge,
Oh,
or like some, with like, the difference in the property or something?
conditions.
Or, oh wait, boundary conditions, it has to equal something at that boundary.
Right, so two values have to be the same at some boundary, right?
Okay.
And so when we think about this in the context, like, let's say we're talking about fluids, or we were talking about computational. We used to say, for example, there was a no slip boundary condition, right? So let's say the very bottom of our pool had a no slip boundary condition. What did that mean? The velocity at z equals h or z equals 0 was 0. That's the definition of a boundary condition. So here I'm going to ask a question about a boundary condition at a boundary that's permeable. Okay, so something's going to pass through the boundary. And the reason that I drew this type of business up here is because I wanted to start us thinking about, okay, here we have a boundary condition, right? And we said, okay, omega is the same across them, fine, so be it. We'll talk about that more when we think about a wave coming at an angle. But what were the conditions that we had, say, on E and B at a boundary?
They're, you know, read these.
For the perpendicular one and then parallel one.
Okay, well, tell me the parallel one first.
Oh, okay. For E, E one equals two at the boundary. And then for B, the B one over mu equals mu.
That,
And then the perpendicular one.
we'll get to that.
Slow down.
Okay, so you can find the perpendicular ones probably in your notes. So let's look at this one then. So E has that form. Do I have a way of writing, say, a z equals 0 and t equals 0 time this is equal 0? Equals 0 here. Is there a way of relating E across this boundary? Yeah, okay, good. And let me ask a different question. Is there a perpendicular component to E? What's that? So you're thinking of the wave, and that's correct. K would be perpendicular. But thinking about the B, why are you both saying no? What do you know that you haven't told us? Oh, you're saying that the wave is coming at the wall, that it's like a giant board being pressed this way?
Yeah,
Do people all feel that way?
it's like up, down.
Oh, in one person, does that make sense? Kind of, okay, let's think about this again. We're gonna do this. The direction of propagation is this way. E and B are this way. Okay, do they have, say at this boundary, okay, do they have a perpendicular component?
Yeah.
Yeah. Slow down.
No.
Yes or no, you show me.
E is up and down, so it's never gonna be like this way.
E is up and down.
Same as.
So thinking about the boundary as a wall like this, and E is up and down. The direction of E goes up and down, up and down.
It's never gonna be perfect.
Is there a perpendicular component? So do we need perpendicular boundary conditions? No.
Sick.
Not bad, right? But we will need this when we come in at a angle. Yeah, I know we're gonna do that, right? Get that out of here. Okay, and so then Isabel already directly pointed out, she said, well, of course I know how to relate E1 to E2, right? So let's look at this first section here. Does that make sense why I wrote it that way? You get that this little piece here gets to come along. Because it's the other boundary condition coming back, right? To account for it. So recall that the system is set up. Right? We're imagining if time equals 0, at this location, boom. All of our exponentials are gonna disappear, they become 1, no big deal. We're just adding together these boundary conditions. And we know in our head that this is a standing situation. So even though the waves have moved through, they're at equilibrium, right? So you can think about it in the context of this light is not a pulse of light that I then need to track all the way around. It's continuous. Okay, so I can just add them like this.
So that's at the first boundary.
So that's adding these ones to these ones. I may have wrote it differently. Yeah, sorry. I'm gonna be bad at tiny lettering because it's a lot of tiny lettering. All right. And I can use this bottom one as well, but I'm gonna keep in mind our favorite little new rule. Right?
What does the O mean? O.
That's like the amplitude, so I wrote it like E naught. So like the whole E is it's that plus the wave, whereas this is just like how big does E get? Right? And so in general, I'm thinking of that in the context of like, if I'm getting light, it's either a little bit of perturbation of my E field or a big perturbation. But either way, that light is moving towards us like this, right? Boom. So that's the first one. That's the first boundary condition. Okay. I might say like C. Second boundary condition tells us this side we're gonna remember treat that mu naught and these mu twos are
Probably equal.
they're probably equal. Good, exactly right. And it's much more likely that these are the ones that are going to change it. Okay, so let's do that.
Yes, one by about taking the one, but it's the PLI, because there's only one PLI.
That would help me.
And it makes it more confusing to have the one, because the eye looks a lot like teeth.
Let's do erase everyone, stop writing it.
You gotta write, you have to write notes in pencil, right?
No.
No? Oh my god, the world is so different from when I was young. Okay.
If I make a mistake, I can't.
Yeah, wait, I do need it there though. So there's a second and that's it. Okay. Alright. Is that okay?
On the first one, it says EOR, what's the name of that one? Is that one?
That is the same. Yeah.
Oh.
Okay, so this one gives you this one. Sick. Yeah.
What does mean in the context of boundary conditions? Oh,
One of
What
them.
is this?
oh, it's the relativity of the magnetic field.
That's right.
Yeah, we think about it in terms of like how polarizable is the material,
Oh, thank you.
magnetically polarized.
Understood.
How well does the material?
But EOT, that's steel one. EOT one or no?
That is one.
It is.
Come on now. Okay. Good. This is how you know the students are engaged. And they start correcting your work. That's why I make mistakes on purpose. It's definitely not on accident. So, okay.
I should tell everyone that I'm on my tabs too. I make mistakes just to make sure the professors catch it. That's not it.
Okay. Well, we don't need to be tested. Oh, right.
Learning is a lifelong
Keep on the
process.
toes, you know?
That's true. Maybe you're learning more by teaching.
Yeah.
How that you're learning.
Yeah.
Real metacognitive. All right.
Do it all wrong.
Okay, let's imagine that this is Z equals D. Okay, still gonna take time equals 0 here. Just imagine time equals 0. So now what does E look like? Just generally speaking at that location.
It's still parallel.
So just thinking about it in this context here. P equals 0, this piece equals 0, and this equals P. Okay. Let's just write that for 1 second so that we can see something really important. So E is E naught, E, the I, A, D. Okay. So this is something that we have to remember because now we are matching amplitudes and D is going to be modified by K. Okay. So if we're going to be looking at that, we can write that whole thing again. But on this left-hand side, everywhere that we wrote EOI, we're now going to have
Also,
yeah, some extra crap. Perfect.
like,
What? You said lame? Okay. All right, so let's write that extra crap. So at that second boundary, how are we gonna write it?
right here. Here,
E-O. E.
one,
Is it
and oh. Well,
Is it 1 or 2, folks?
it's one,
It's 1, okay, good.
and then little e to the IKD,
Is that it?
and then EOR two.
Is that it?
All for the all program.
Wait, what are you asking?
Okay, so I'm asking at this boundary. I need to add up everything on the left-hand side is equal to everything on the right-hand side.
So if you
EOR two
equals,
plus U. No, the R.
So this one?
Yeah.
Yeah, okay. I thought you said equals ER2. My bad.
Plus.
My bad.
Yeah.
Get it right in town. Okay. Is that okay?
Equals. UT two. And then. IKD.
Okay. Now, what have we missed? I got rid of it, I literally erased it, so you have to think.
That's good.
Velocities are gonna change, you're right, that's taken into account here. Anything else gonna change? Direction. Is the direction gonna change?
No.
When we have a reflected wave, we're accounting for that already good?
Oh.
The index is changing. Well,
Index of what?
the material that we're like phasing through.
That's there, right? N1, N2, N3. We haven't used that information yet.
Right.
How did I open up this class? What were we talking about? I know it was many, many hours ago.
String,
String. And what was I asking about?
whether its frequency was the same.
Okay, and does it?
Yeah.
And what property changes instead?
Direction.
Inverse.
Well, that's changed.
The direction did change. We had a reflected one and one of them was inverted, right? Okay, well, what was the thing that I was trying to relate between frequency and there was another property of the wave? The wave number. Why does the wave number change?
Okay.
Ah, so the K's cannot be the same between boundaries. We didn't care about it there because the K's disappeared because we chose Z equals 0. Right? So we got a little smart. And then we got too smart for our own good. So whatever this started with, K1, changed to K2. Right? And then when it comes out of here, it changes to you see? Or no?
You never wrote that on the board.
You never wrote that.
You said you already, you said.
I don't know. So what I wrote on the board was that the frequency, right, is not going to change. Okay? And if that's the case, how do I relate these three properties?
With the square.
They just equal? Finding it, he's got it in the notes. Go, Rolando, go.
Yeah.
Omega over 2 pi is equal to frequency. Oh wait, yeah, they do this, this omega is equal to kb, I'm just gonna call that v.
Then that is a v. This is the velocity, because we said that the velocity changed, right?
Yeah, so k is equal to w.
That's what is v equal to.
Plus.
The speed of like,
So omega is.
Omega is equal to kv,
Yes.
and so it's v equal.
I was plus.
Omega over here.
is it V or is it frequency? Okay, okay.
Yes or no? I don't know. Okay, so omega has units of 1 over time, and k has units of 1 over length. So now this has units of length over time, which is what a velocity is. Okay, so in fact, I said this is not going to change. Right, that's the first thing I said in the class, more or less. And yet we know this is changing. So therefore, this has to change likewise. So let's just put that in a little box and put that aside for later. All right. So let's finish the notation here. So what am I missing?
1, 2, 3.
Where's the 1?
First K.
No,
The first one, there were two instead of.
The first two have to be twos, remember? Because they're propagating in the glass, and the glass is two. And these are threes. Bada bing, bada boom. Okay, good. So let's play that same game again. I'm not gonna bore you with the details, but it looks like this. I'm gonna get these letters on, so whatever. That reddish? Okay, so how many unknowns do I have? Far afraid. Too many unknowns, perhaps.
There's a way to relate some of them together.
Yeah, I mean, I really need to know this, right? And I have this somewhere. Just want them in terms of each other more or less. Right? So I have 1, 2, 3, 4 equations. Right? And then I had a couple equations here, right? That related E on one side to the other.
So we get these systems.
What's that?
Yeah, these systems.
Yeah. So we're gonna end up writing something like ET3 as I wrote it over there over EI1. Sorry, horrible notation. And that'll be some function of all of our velocities. Velocity 1, velocity 2, velocity 2. Okay. And the only thing that's really important to keep in mind that when you do go to write this, consider if you want to cosine and sine.
What looks better?
No, it's just easier to work with. This is obviously easier to write the first time, but when you want to go solve the system equations, cosine and sine will look better. You'll see. Maybe. Okay. Success? You can do it on your own. You should. Okay, that's fine. So it's a Tuesday. And we'll have a office hour after this where we can walk through it in more detail. Okay. So I just went on this huge tirade about case, right? All right. So now let's do the thing that sucks. Right? This doesn't suck already. Goes in like this. Now what happens? What? Perpendicular what? We have E components that are perpendicular. Okay. Now we have more boundary conditions. Oh, okay. So let's work through it. Ready? We're gonna set this one up because we only have like 15 minutes, but it'll be fine. Can I get rid of this one?
Yeah, so.
No one wants to see it anymore, right? It's just the homework problem. It's okay. It's, we're only gonna do 2 this week. Yeah.
Yeah, it's with the for testing and stuff in the strikes.
Oh yeah, 95% of faculty said that they want to strike.
So they get like one more chance to meet the new.
Well, so what happens is a strike authorization is considered a work action. So the way that unions work is they're only allowed to do certain actions that are protected by labor law. So we can't just decide to stop working on Tuesday, right? We'd be like, oh, I'm done working. No, so you have to like apply to do a strike and like you have to get right through all those legalese. And there are many different like facets of the process of going towards a strike. And in each one you have mediation, right? So we've done fact finding, they're negotiating, right? And usually what they're trying to determine when they call for an authorization of a strike, which is asking all of the faculty members who are CFA members, whether or not they would be willing to strike, is how many people are not going to come to work. So when 95% of people say we're not coming to work, and then management says, well, it'll be a little hard to keep the university open if we don't have any faculty members, right? And that includes lecturers, right? Lecturers are considered part of the faculty, even though they're not tenure. Okay. So unfortunately. For you, right? That could impact the semester. Because I won't be able to answer emails, won't be able to grade, won't be able to do anything regarding your education. Part of a strike is no work at all. Work stoppage. My hope is with the 95% that they'll just be like, fine, fuck off, right? We'll give you your money. We'll take maybe only 25% bonuses instead of 30. Well, there we want 12 instead of 4, right? Because the cost of inflation. And they're like, well, we don't have any money left because we only have $8 billion in reserves. That's so great.
Really, there's a lot of money.
Say the strike for long as this semester, then what happens? Like we all said fail.
No. So it won't be nice, but your grade would be locked at what your grade is.
Oh shit.
Oh, don't say that to me. So, you know, the thing is I wouldn't be able to teach another lecture, right? Let's say that strike happened tomorrow. I wouldn't be able to teach another lecture. I wouldn't be able to grade any of your work until the strike was resolved. Now, that being said, you could work on your own, right? There's nothing stopping you from doing that. So if I sense that the strike was coming, I might assign the rest of the homework. But I also think that that would be insane because I can't expect you to open up Griffiths and read it and be like, oh, I get it just as much as when Dr. Guzmán was talking. It's fucking bullshit. It's better than nothing, that's true. But you know, what we would do is we would have to say either grade you on what you were able to do, right? Just like imagine, let's say the school closed down because there's like a deadly virus, right? Maybe some of us lived through that, right? So what happens in that situation? Right? Are you penalized for that? No.
Yeah.
Yes, okay, yes, you are. Yeah, certainly. But at the same time, we try not to have it happen, right? We have to be accommodating. So I couldn't just fail folks because, oh, you missed 2/3 of the assignments that I wasn't able to give you. Right? Like that's insane. So I would grade you based on what I had. Right? And I'd give you an opportunity to determine anything that would improve your grade up to that point. My hope is that this doesn't happen.
They listen.
Yeah, we'll see. Well, good vibes, everyone.
Yeah. It's good.
All right. So let's talk about what's now totally on your mind. All right. So we have a wave. Okay, let's call this K1. And I know this is gonna be really annoying, but we're gonna have different notation all over the time. Okay. K1 is coming in. Okay. We can break K1 into. Very good. And so this will be K2. And this will be K3. Okay. So K2 is incident to the surface. Therefore, K2 perpendicular. And K3 parallel. Okay. That's from,
You've got that K too.
oh.
Yeah, I'm.
Oh. Yeah, no, that's okay. That's fine. Does this make sense or no? Okay, so let's think about our boundary conditions here. If K2 is incident to the surface, then E for K2 looks like correct or incorrect? Considering just the K2 component. If we can break apart any wave, right, let's think about this for a second. Okay, I have some wave that's going like this. Right. So what does that allow me to do? It allows me to think of it as a wave going this way and a wave going this way, and we just add them up together good. Okay? Okay, so let's first treat this way. Have we done this before? This is what we just did. And we said E and B are plane waves, and they're parallel to the wall. Good, okay. So let's write that down. So E. Parallel is E, parallel, no one cares, good. Okay, what about K3, which is parallel? So now E and B are correct. Very good. All right. So someone had some really good boundary conditions for us.
Like saying to each other.
Oh, no, sorry, just to the boundary.
Okay, that's why I was confused. I was like, you're lying right now.
You're right. Okay, so yeah, so let's think about this in the context of they're not perpendicular to one another, right? So the wave is traveling this way, okay? So this is the wave going upwards, and here's EB plane, and EB plane is now perpendicular to the boundary. So in K3, E and B are perpendicular, and I should maybe just say to the boundary. Okay. Okay. So what is the boundary condition for perpendicular E and B?
The phone times, one.
Oh, right. Anything else?
And then, B1 to.
All right, so let's rewrite this one. So E1 perpendicular is epsilon 2 divided by epsilon 1. E2 perpendicular. And you know, this thing is like more or less N2 over N1 quantity squared. Another way of writing that would be, you know, the V's. You remember that one? Let's just write that down right over here. Here's another box for shit to remember. V equals. Right. So therefore. Simple. Okay. So if I have, oops. Okay, good. Okay. All right, so what does this mean? What the hell have I written?
Wrote an approximation.
I wrote an approximation, good, and let's read the approximation. So this is N2. This is N1. If they're the same, what happens?
Nothing's changed.
There's no reflection.
Are we talking about reflection?
No, we
What are we talking about?
just equals.
Just talking about E field. So let's think about this again, right? So this piece, no matter what, right? That's this one. That's gonna be the same. And we know how to do that left, right. Maybe there's reflection, maybe there's not. We don't care about that. What does this one say?
We can use it to find the fractions between the each.
Yes, and we will do that in a little bit. But what I'm asking here is on the left-hand side, I have an amount that's going up, for example, right? Just because I've drawn it this way. And on the right-hand side, I'm asking how much is still going up afterwards. If they're equal, then of course you get the same amount still going up. Nothing surprising. And what about if they're not equal? What if N2 is larger than N1? So again, so E1 is your original, and E2 is your final.
Bigger.
Work through that again. E1 is your original, and E2 is your final.
And
That's just bigger.
Yeah, so let's say N2 is twice as big as N1. What's that now?
E2 is 4 times smaller.
The fractions come back for us. Okay, so that's really important to remember. If N2 is larger than N1, right? Then this becomes a large number, and this has to be a small number for the equality to be true. Okay, so even when we just double it, we've shrunk the amplitude in E that's going transverse to the direction by a factor of 4, right? Damn. So what happens if it's 10? God damn. Okay, so what happens then? So let's say you have something on the right-hand side, you have 1. And on the left-hand side, sorry, let me do that backwards. The left-hand side, you have 1. The right-hand side, you have 10. Okay, so now I have a wave coming in like this. And it has some component this way and some component this way. What happens to this component? Basically nothing. We don't really give a shit, right? It goes through. Okay, what about this component? 100 times smaller. So let's draw that. Okay, so I have these two here, the same size, and 100 times smaller is like that, right? That's not a really good drawing. But you get the idea. And so what does that look like? Bending of the light. Whoa, whoa, let's go, boys. All right. And everyone as well. Not just the boys.
Yeah.
Right. Does that make sense?
Yeah.
Yeah? Okay. Oh God, this is so much better. All right.
2 and 3 minutes.
2 to 3 minutes. All right, let's generalize really quickly. Okay, so what am I doing here? I'm writing down K and R in terms of this arbitrary direction. And I can say this, where K dotted into R is the component of K in the direction R. And I'm choosing R just arbitrarily, okay? What I mean by that is that this is going to be completely generalizable. I can point R in any direction I want, and I can ask how aligned is K to that direction, okay? So I can write E is E naught E to the I K dot R as opposed to KZ minus omega T. Okay, and that'll be in what we call the n hat direction. Okay. All right. So now I have some boundary on the left-hand side and 1 on the right-hand side, and I can write something like this is bold, but maybe stupid. All right. So on this end, all right, E1 is E I not or K1 dotted with R minus T. And then this one. Right. Same stuff we just had. On this side. Let's be look careful here. So this is your incident waves. Not one, but your incident waves, K. Remember that it consists of this and that. Whereas this reflected one is now going to bounce off of the interface. And may or may not share the same properties. Okay. I'm gonna write it here, little r. So there's KR, there's KI, and there's KT. Okay, and then on Thursday, we're gonna see how they all relate to each other. And we're gonna derive Snell's laws of reflection. Sick, right? You'd be like, why not just come with that? Because maybe you work at a game developer and you make a lot of money later. Doing scattering. Okay. Questions, comments, concerns? 30%. 30%.
No more bonus.
Oh, no, I want a bonus. I just don't want them to have a 30% bonus. And then for them to cut salaries and cut student, like, we're not even hiring that much. No.
I think I had an email like raising tuition.
Yeah, they're raising tuition to give them some bonuses. That's right.
Yeah.
It's just sales big.
You're gonna raise tuition, give me a bonus, you know? Yeah. Yeah.
Well, what section is that book that is covered?
So this is still not 9.3, I believe. We don't really get to 9.4 until we start talking about what it means to have a wave with charges that can move around.
Okay,
Because then we'll start to think about what happens when the charges move with the wave.
okay.
Oh, he's so pissed. Does that make sense?